So far we've been looking at exponential functions, and we saw that logarithmic functions were inverse functions of exponential functions and vice versa. We looked at properties of the graphs of those functions. And so now we're going to look at some properties of logarithms that are going to be able to help us solve these logarithmic equations that we're going to be looking at soon. So in front of us are the properties of logarithms, the objectives that I would like you to know by the end of this lecture and going through some homework. You should be able to work with the properties of logarithms. You should be able to write a logarithmic expression as a sum or a difference of logarithms. So that is something that we'll do in this class, but you'll be using that a lot in calculus when you are trying to differentiate a logarithm or integrate a logarithm. It's helpful to be able to write one complicated logarithm as a sum or a difference of logs. The one that we'll be using a lot in this class to help us solve are writing a logarithmic expression as a single logarithm. So we might have a sum or a difference of multiple logs, and we want to rewrite that as a single log. So I'm not sure if this is still the case, but in the past, calculators, you could only have logarithms with base 10 or base e, or natural log. And so being able to use the change of base formula to help us evaluate logarithms. So evaluate logarithms whose base is neither 10 nor e. Okay, so let's look at properties of logarithms. I don't have probably time to prove all of these, but we can look at some of them and proving some of them. So properties of logarithms. So the first one on here says if we have log base b of 1, this is equal to 0. Before we even show that, let's go back and look at what the definition of a logarithm is. So for instance, if you had y is equal to log base b of x, this is equivalent of writing it as the base of our log is the base of our exponential. This is if and only if. B raised to the y power is equal to x. So there were a couple stipulations that had to hold in order for this to be true. Our base had to be greater than 0. Our base could not equal 1. And what we were taking the log of, so this x, has to be greater than 0. So looking at this first property that says if we have log base b of 1 equals 0. Well, if you rewrite this in exponential form, this would be saying our base b raised to what was on the other side, 0, is equal to 1. Well, anything raised to the 0 power other than 0 is equal to 1. So we can see that this is true. The next one that states log base a of a is equal to 1. So if we rewrote this in exponential form, this is saying a raised to the first power is equal to a, which is also true. So here, if we have log base b of m times n, then we can rewrite this as a sum of 2 logs. So if there's multiplication in between our argument is m times n, then we can break it down as a sum of logs. Log base b of m plus log base b of n. So multiplication in between makes addition to rewrite it as a string of logs. The next one states that if you have log base b And then your argument, you're dividing. You have m in the numerator divided by n in the denominator. And this is equal to log base b of m, so our numerator, minus log base b of n, so our denominator. So division in between. And our argument makes the log a difference of 2 logs. The next one that we have is if we have log base b, a raised to the m power, then what we can do is we can bring that m down in front of our logarithm, and that would be m times log base b of a. So we're going to use this when we have a variable in our exponent that we're trying to solve for, and we are not able to manipulate our bases to be the same like we were seeing the other day to solve exponential equations. We could take the logarithm of both sides and use this property where we could bring our exponent down. But we'll see that later on in this class today. And then we have the following. If we have a log base b of a, that is equal to log of a divided by log of b. So this is actually the change of base formula. And we'll talk about that again in a little bit. And then the last one is if we have a raised to log base a of x, then this is equal to x. This has to do with these being inverses of each other. So if we had f of x is equal to a to the x, then f inverse of x we saw was log base a of some value x. So recall, in order for two functions to be inverses of each other, we have f of f inverse of x must equal x. And so if we go in here and we substitute in f inverse of x, wherever we see an x in our f of x function, this would be saying a raised to our log base a of x. This has to be, by definition, of being inverses of each other, x. So it should also be able to go the opposite direction. So if we had f inverse of f of x, this also must equal x to be an inverse function. And so let's go in wherever we see an x and f of x, let's drop in a raised to the x power. So doing so, we would have log base a of a raised to the x power. This also is equal to x. So this one looks a little, makes more sense than the other one, possibly. This one I can see by just going back into with the definition that here my base a raised to the other side, x, is equal to a to the x power, which is a true statement. Okay, so we have an example in front of us. We have the natural log of the argument, which is x times the square root. Underneath the square root, our radicand is 1 plus x squared. We're given the stipulation that x has to be greater than 0. So that makes sense in the fact that we were looking at the domains of logarithms before, and we knew that we could only take the logarithm of a positive value. And so in that case, x would have to be greater than 0. If it was negative, we would have a natural log of a negative number. That being said, we want to rewrite this as a sum of logarithms, and anything that has an exponent, we want to write as a coefficient in front. So I notice here that I have multiplication between the x and that square root. And by that property, if there's multiplication in the argument, then we can rewrite it as a sum. So this is the same thing as the natural log of x plus the natural log of the square root of 1 plus x squared. So recall, you can rewrite radicals as rational exponents. So recall, if you have the square root of b, this is the same thing as b raised to the 1/2 power. If you had the nth root of b, this is the same thing as b raised to the 1/n power. Just to review real quick. If you had the nth root of b raised to the m power, we can rewrite this as a rational exponent as b raised to the m divided by n exponent. And so these are rules that you're going to see again and again, especially in calculus. You're going to want to be able to rewrite radicals with rational exponents. And so based off of that, we can rewrite this radical here as a 1/2 power. And so we have the natural log of x plus the natural log, parentheses, of 1 plus x squared. And that 1 plus x squared is raised to the 1/2 power. And so one of those properties of logarithms was that we could take an exponent and we can bring it down in front of our log. And so this would be the same thing as the natural log of x plus 1/2 times the natural log of 1 plus x squared. Okay, so that's as far as we can take that. Common error students like to make is if they see a log of any base and they see some sum in between our argument, they want to distribute that log. But log is a function. It's not some coefficient or variable that we can distribute. So this is not equal to log base b of a plus log base b of capital B. So don't do that. So let's look at a couple more examples. So our next problem, we want to expand this as a sum and difference of logs, no exponents. We want to rewrite those as coefficients. And here we have the natural log. Our argument is x minus 4. That quantity is all over x squared minus 1. And then that fraction is all raised to the 2/3 power. So first thing we want to do is we want to get rid of that 2/3 power. And it's an exponent, so we can use the properties of logs where we can bring our exponent down front. So this is the same thing as 2/3, the natural log of x minus 4. And that x minus 4 is all over x squared minus 1. We have division here. And so division makes us rewrite it as subtraction. Be careful though, because we should have parentheses around this whole thing, that 2/3 out front. And so we have the natural log of x minus 4. Division is minus the natural log of x squared minus 1. And that's as far as we can take it, because again, we can't distribute that log. So let's go and look at an example where we're going the opposite direction. So we're given a sum or difference of logs, and we want to rewrite it as a single logarithmic function or expression. So going in the opposite direction, this example, we have log base 3 of the square root of x minus log base 3 of x cubed. So having that minus in between our two logarithms, make sure that the bases are the same. If they are not the same, we couldn't be using these properties, which they are. And then we're going to rewrite this as log base 3. Well, subtraction, so we're going to have square root of x in our numerator all over x cubed in our denominator. So we can use rules of exponents to rewrite this and simplify it down. So recall, if you have the same base and there's division, we can look at if n is greater than m, then we would look at b raised to the n minus m power. Or if we had the opposite, if we had m is greater than n, this can be the same thing, but let's bring it down to the denominator. So 1 over b to the m minus n. Or you can just do this first piece, and if that was not a positive number, then remember that if you had a negative exponent, we could rewrite it. If it was in the numerator, we can rewrite it and put it down in the denominator. Or if we had a negative exponent in the denominator, we can rewrite it, make that exponent positive by bringing it up to the numerator. So thinking of those properties, let's rewrite, first of all, the square root of x as an exponent. So this is log base 3 of x. This is raised to the 1/2 power all over x cubed. So I have the same base, x. I notice that 3 is larger than 1/2. So I'm going to use my properties of exponents and rewrite this as log base 3 of 1 all over x to the 3 minus 1/2 exponent. Getting a common denominator so I can subtract 1/2 from 3. Well, 3 I could rewrite as 6/2, common denominator of 2 with a 1/2. So 6/2 minus 1/2 is 5/2. So this would be the same thing as log base 3 of 1 over x to the 5/2 power. So this is a property more that we're going to be using today when we're solving logarithmic equations, trying to solve for our variable. We're going to be wanting to be able to rewrite a sum or difference of logs into one logarithm. So the example in front of us is 3 times log base 5, the argument parentheses 3x plus 1. And that argument, and then we have minus 2 times log base 5. The argument is parentheses 2x minus 1 and the parentheses. And then we have minus log base 5 of x. So let's first start by taking our coefficients that are in front of our logs, and let's rewrite them as exponents. And so doing that, that 3 in front of the log base 5 is now log base 5, parentheses of 3x plus 1, and that is cubed, minus that 2 in front of that log, we're going to rewrite as an exponent. So it's log base 5, parentheses of 2x minus 1, all squared, minus log base 5 of x. So this minus in between tells us division. And so let's just combine those first two logs. We have log base 5 of 3x plus 1 cubed all over 2x minus 1 squared. And then we have outside minus log based 5 of x. So again, we have subtraction in between. And so we can rewrite this. Subtraction again is division. So I have log base 5 of the fraction 3x plus 1 that is cubed, all divided by 2x minus 1, and that is squared. And this is divided by x. So we don't like complex fractions, fractions with in fractions. We can rewrite this. Recall if you had two fractions, a divided by b, let's say that's all over c divided by d. We can rewrite this division problem, a divided by b. That is divided by c over d, a over b times d over c. So doing that, knowing that, we can rewrite this. We can multiply what's in our numerator, that fraction, by the reciprocal of our denominator. So this is the same thing as log base 5 of 3x plus 1, that quantity cubed, all over 2x minus 1, that quantity is squared, times this 1 over x. So multiplication with fractions, you just multiply straight across. So we can just make this as a single fraction. Let me just get rid of the 1 up here. So we took a difference of multiple logs and rewrote it as a single log. So there's a couple more properties of logarithms that are going to help us in a minute to solve these logarithmic equations. So the following states these properties, first of all, capital M and capital N and lowercase a must be positive real numbers. And the other stipulation is our base a of our logarithm can't be equal to 1. So we can go different directions. If we are given m is equal to n, then we can basically take the log of both sides of our equation. So if we take log base a of m, this would equal log base a of n. Or we can go in the opposite direction. So if we're given two logs are equal to each other, we have the same base. There's no other constants out there floating around. So a log equal a log. And then we can say that the argument m must equal n. Okay, so we'll be seeing the property in just a minute. So we're going to use these properties, and I'm going to create another video solving logarithmic equations and exponential equations. So we'll see that in that next video.